Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHG2 Cloud. And today I'm really happy to announce to you our brand new, long-awaited method to calculate the required borefield size. Now, today is also the last big update of GHG2 in 2025. But in 2026 there will be way more to come. But first, let's dive into this new method you've all been waiting for. So as you know, GHG2 has no limited set of borefield configurations. You can design whatever you want, change the spacing in length and width direction, or even go full on with coordinates and design up to 5,000 boreholes wherever you want. So it's extremely flexible to design. So that makes also the design that it requires some iteration. For example, what you typically do is you make a design, you calculate the temperature profile, you update your design, you again calculate it, etc, etc. And this gives quite a lot of insight, especially in the borefield physics. But yeah, it is sometimes time consuming, especially if you're new into the world of borefield design. So another option is that you just say, okay, we start with a certain number of boreholes, a certain configuration, and let the algorithm decide how deep I should drill. This works, but there is a problem that perhaps your number of boreholes was not optimal, and your total borehole meters is larger than it actually needs to be. And there is also the risk when you're having quite high cooling peaks, cooling load, that you end up with a gradient error, and that there is no theoretical solution. If you have not read about the gradient error, it's also linked in the description below. So, what you've been demanding or requesting since we started GHG2 Cloud, or we launched it last November, it is to say in 2024, is, well, isn't there a method to calculate the required depth and borefield size? So, the idea is that you have an optimization algorithm that determines for you the minimum total borehole length. And the idea is that you don't need as much manual iteration and trial and error, that you just say, this is my available space, what should I do? But the problem is that since we do not have this pre-configured configurations, it was really time consuming. There are thousands and thousands of options to be checked. And even if each of them took 3 seconds to simulate, you easily can end up with hours of simulation. So it was not feasible up until now. So today I'm really happy to launch and publish this new method for all GHG2 users and all licenses to automatically simulate for you and calculate the required size and borehole depth. So the idea is that you start with a certain footprint, the area you have available, that you specify what your minimum and maximum allowed depth is, where the optimization should stay within, as well as your minimum and maximum borehole spacing. This method also uses regular configurations. In the future it will be updated to random borefield configurations, but now it's regular to make it really fast. L-shaped, U-shaped, box, rectangular and dent shaped. And the idea is it will just calculate the optimal solution, or all the possible solutions, with the minimum total borehole length. Now, there were 2 big advancements we made over the last months that made this possible, namely the implementation of an artificial neural network, which we discussed last time, which made the simulation of the required borehole depth way faster, and the concept of Bayesian optimization to actually find the optimal solution. Now, if we look a little bit deeper into this Bayesian optimization, without going too much in detail because it's a rather mathematical subject, we know that in this method we have to optimize quite a lot of things. We have to find the optimal shape, the number of boreholes in the length and width direction, the spacing in length and width direction. And there are a couple of ways to do this in the optimization world. And 3 of them are given here below. So the first thing you need to know is that for all these parameters, the shape, number, length, width, spacing length, width, etc. So we have 5. This is called a hyperparameter. So it's something we can change, and that will have an effect on our result, namely our minimum total borehole length. And this is here given in 2D as an example. So one solution could be to just say, okay, let's take a couple of values for each parameter and just simulate all the combinations. And this is called a grid search. We simulate a regular grid where both parameters are evenly spaced, and then we take the lowest value of all our simulations. And this is really time consuming, and if you want to have an accurate result, you need to have quite a lot of variation in all the parameters, and you end up with, again, thousands of simulations, and even with an artificial neural network, that takes too much time. Another solution can be, instead of working with a regular grid, is that you just say, okay, I want to do 100 possible combinations, and it just takes random combinations of all the input parameters and calculates the required total borehole length, and it returns you the minimum size. This again has the same problem as the first option, is that you just try certain things, and since it's random, you also do not always know whether you're in the optimal solution or not. The last one, which is called Bayesian optimization, it uses a statistics-based methodology. So what we do is we start with a couple of tries, so we do some random simulations, and based on that, we already know which combination of shape and spacings and number of boreholes leads to a good result and which combinations do not. So we know that we can search in the neighborhood of the good simulation and stay away from the bad simulations. And so we converge towards what is statistically the best solution. And this is also shown in this graph here. So we have our dotted line, which is our total function, let's say, of the total borehole length for every combination of input parameters. And it's of this function that we want to find the minimum. So what we do is we start by random selecting configurations and simulating it. So we know at this simulation the exact value, the exact total borehole length. So here there is no uncertainty, we know this value. But the further you move away from a simulation, the bigger your uncertainty gets. If my configuration is rather different than the one I already simulated, there is quite a lot of uncertainty on what this value actually is. And for our next iteration, so our next guess, in this case it's iteration 3, we want to search the point where we have the highest or the highest chance of finding a better solution. So if you look at the uncertainty bounds, we see that this point here, as also shown in the orange line, is our best chance of finding a lower solution, because our lower uncertainty bound is lower. So we do this, then we know the exact value there, and we now see that our new best guess is actually on the right of our initial point. And so we converge statistically towards a point where we have the highest chance of finding the minimum solution. Now it is important to say that since we have a very non-convex problem here, the optimal configuration problem, there is no mathematical certainty that we end up in an optimum. The only way is to try everything, but that takes hours. And with this Bayesian optimization, we have the highest chance of being in a very good solution. But that also means that if you run this simulation over and over and over again, perhaps sometimes you end up with other configurations. And the reason is that the first step of this optimization is starting with random points. And since they differ in each simulation, perhaps they converge towards a slightly different optimum. But we believe that this method is actually the fastest and the best way of giving you an accurate prediction of what the best configuration looks like. Now, so far the theory. Let's jump into GHG2 Cloud and show you hands-on how you can use this method and why it can be powerful for your projects. So here we are in GHG2 Cloud. I created a new project, and as you can see, we have here a new aim, the calculate required size and depth aim. Now, for this exercise, we will just keep everything constant, our borehole resistance, our thermal demand, our ground load, etc. But instead of calculating the temperature profile, I'm now asking, well, calculate for me, for these default settings, the required size and depth. And if we now go to the borefield app, it's totally changed. And we can no longer select our number of boreholes, etc. We can just say, okay, the algorithm can select all these different type of configurations. So we allow it to pick whatever it wants. We have our buried depth, our borehole diameter, and then we have ranges where we can select the borehole depth. For example, you say, okay, we cannot drill deeper than so many meters, or on the other hand, we do not want any solutions which are above 50 meters, it is to say shallower than 50 meters. We have the same with the borehole spacing, and that's all the borehole, the borefield input parameters. On the other hand, you have optimization settings. So for our Bayesian optimization, so of course we need a certain footprint. What is the available size in meters? We need to set a step size for borehole spacing. So for example, we here have 5 to 7 meters with a spacing of 0.5. This means that both 5, 5.5, 6, 6.5, and 7 are valuable solutions to our problem. Then we have two other parameters, the minimum and the maximum number of boreholes. This is not really necessary for our simulation because it will determine it automatically. But if you know we have a small project, it will be no more than 10 boreholes. You can play a little bit with these bounds to speed up the simulation, because it will not spend time trying configurations that do not make any sense. And then our last option is what I told before, has to do with this number of searches. So the more tries you do, the better your final answer will be, or the higher the chance that you will end up with the best solution. So let's now go ahead and calculate this scenario. So just to say, for most cases, this 100 is more than enough, and even in the case like here, 50 probably also was enough, since it's a rather small configuration. So now it will run through 100 trials and give us the best solution. So that's already done here. So what we see below is all the possible combinations. Here we have 36 of the algorithm, sorted from lowest borehole length to the longest. So we have our 487 U-shaped solution, which is actually simulated here. This is the optimal solution the algorithm found, and our worst solution is 588. So these are all the combinations the algorithm has found. And as you can see, there are all tildes before the length, and that means that it's approximate this borehole length. And the reason is, as I said before, this algorithm uses an artificial neural network to speed up the simulations. But as we discussed last time, as linked in the description, this gives a certain uncertainty. So there is a range between 1 to 5% of uncertainty, but it's way faster. So that's why we did it. And the order of the solutions, according to us, is still accurate, but perhaps the absolute value, it's not 478, but slightly different. And that you can also see here, we're not exactly within the limits of 2 and 17. We are slightly below this, so our borefield can be changed, can be a little bit smaller perhaps, or a little bit shallower. And one way to do that is in our general tab, you have this option here to accurately calculate the optimal configuration. And what this will do is it will run the optimization strategy again, find the best solution, and before it returns it, calculates the required depth for that configuration without a neural network. So you still have all the other options if you want, but you know for sure that your first option is actually optimized. It is or accurately calculated. And that's what you see here. So we now have a borefield configuration which exactly fits our temperature limits and which has a slightly different borehole length without a tilt because we now calculated it exactly. Now, as you can see when you look at this results, it's not the same table as before, and that's because, if you recall, the first step in the Bayesian optimization is actually trying out a couple of simulations, trying out a couple of configurations. And by doing so, by trying out the different combinations, it can be that it converges towards a slightly different optimal solution. So if you run this simulation over and over and over again, your table probably will change a couple of times. But as you can see, our solution here, it's close to the one we had before. So it does not really matter in the end because it's a good estimate of what you should do. And in our case, the best possible solution is 448 total borehole meters. Now, if you, for example, say I want to simulate, what are we going to simulate, for example? Let us simulate here a rectangle field. You can double click on it and it will load all the parameters into a new scenario where you then can just say, well, let's calculate the temperature profile. And we see in this case, it was exactly accurate, but we have a different solution. So that's everything I wanted to say about this new method. I hope you found this really interesting. I think it's especially useful if you, for example, for your borehole resistance, you put your flow rate for the entire bore field. So then it will also automatically take the borehole resistance into account, and that having less boreholes can create more turbulence because you have a more flow rate, and quite a lot of insights you can get from this method instead of just trying it trial by error. So I hope you like our method you've been asking so long for. I hope you consider following and subscribing us, sharing this with your colleagues, liking this video if you think this method will help you with your designs. And I'm looking forward to seeing you in our next video. Take care. Bye.